Very good afternoon. Let's start lecture. All right, let's continue from previous example, previous lecture. We have an example started, but we need to get the chance to finish it. Okay, this is example we started it here. Okay. So for this example, what we want is we want to derive the pulse transfer function. So basically, what the pulse transfer function here is. Or in other words, we want to obtain this expression out of here. Okay. The main two blocks are listed here. So there's a zero-order hold and there's a plant. Okay. So together, these two, you can consider. If you multiply these two together, and then it's basically they are, let's say, some kind of transfer function h of s, right? You can use a single transfer function to represent these two at here. Okay. And in previous lecture, we already derived for zero-order hold. Okay, its transfer function, Laplace transfer function, is 1 minus e to the power negative ts over s. Okay. So that's your zero-order hold. So technically speaking, this h of s is basically 1 minus and then time g of s. Okay, so that's your h of s basically. And you can substitute the g of s that is here, which is 1, like that. So there's SS, so you can one step of simplification. Okay, yeah. So that's specifically what h of s is. But for now, let's just use a general expression. Okay, so you just basically use g of s that is here. Okay. Consider this is a general block g of s that is here. Okay. And then we'll go from here to derive the pulse transfer function. Okay. So I think we did this in the previous lecture. You know, when you have open loop like this, this can be x star of here, and you can think about a fictitious sampler at here, so that'll give you y star at here. Okay. So overall, basically your y of z over x of z, okay, in this case, okay, is actually the h of z transform h of basically h of s, or an expression of h of z that we're looking for here. Okay, yeah. So if you recall in the previous lecture, basically the y star of s over x star of s and equal to h star of s. So when you substitute s with 1 over z log 1 over t log z, and you will get this one here, right? Yeah. Okay. So now we have this h of s, okay, derived here, which is the multiplication of these two blocks. Okay. So basically, we're talking about the z transform of this. Okay, so we're talking about z transform of this one here. Good? Yeah. So here I would say you have a choice at here to do it. Well, anyway, let's continue here. Okay. So let's say what's the Z transform for this expression then, right? What's the Z transform for this expression? Okay. And so let's temporarily group this G of S over S at here. So I'm gonna temporarily define a G1 of S. So basically here this G1 of S is equal to this G of S over this S. Okay? So just temporarily make a symbol representing this G of S over S. And then the Z transform of this portion at here. Just basically you can consider it to multiply this out. It's G1 of S minus ETS times G1 of S. Okay. Yeah. Okay. So Z transform is a linear operator, so it's basically Z transform the first one and minus Z transform the second one. Okay. And then Z transform for the first one. So when you look at the Z transform of any Laplace transform, basically you get symbol wise, right? You'll write down from here to here. And then the second one in here, to that you have to rely on the property, okay? On the property here. So this e to the power negative ts, if you recall that, in Laplace transform, whenever you have a e to the power negative ts times this, it basically represents a delay, right? Or if you think backwards, you know, if you have a, let's say, I have a function x of t or y of t, for example, and then y of t delayed by certain capital T. So y of small t minus capital T, for example. This is a delayed function here, right? And when you take a Laplace transform, all you need to do is you multiply this e to the power negative ts and then times G1 of S at here, right? Yeah. So basically, this quantity here representing one step delay, or one step delay is actually one sampling delay at here. So this Z transform here, so you do have a property here. So that one step delay in digital domain, it's Z to the power negative 1, right? So in digital domain, Z to the power negative. And it's G1S, again, G1 of Z. So that's basically delayed, one step delay, and time this G1 of Z. Okay, so that's this term to here, right? So altogether, you get a 1 minus Z to the power negative 1 times G1 of Z. Okay, yeah. So G1 of Z, if you don't like the symbol here, remember I temporarily use the G1 of S representing GS over S at here, right? So basically, this G1 of S is this quantity here. Okay. So the G1 of Z at here, if I actually go backward a little bit, it's basically Z transform of this plant and divided by S at here. Okay. So that's your G1 of Z basically, right? So if I go back, if I don't use G1 of Z, let's just use the available symbols right inside this block at here. Okay. So your pulse transfer function, okay, and technically speaking, okay, given one zero-order hold and one general plant G of S, then the pulse transfer function is this one. Okay, this is a very useful result because zero-order hold practically exists in every one of the digital control loop. Okay, and it typically exists right in front of this plant, just like this, right? So you have a zero-order hold right in front of the plant, and you probably will have to group this together and then find this corresponding H of Z. Then how do we find that? So this will be the results you can always rely on. It's just 1 minus Z to the power negative 1, Z transform G of S over S. Okay? Yeah. So now back to this specific question. My g of s here is 1 divided by s times s plus 1. So this is a specific plan that here. Okay. Yeah. So let's look at for this specific here. Then what will be the z transform z pulse transfer function here? Okay. So I'm gonna substitute my g of s. This is your g of s at here, and then here's your 1 over s at here. Right? So that's the actual plant, and that's this one. Okay. So with this substitution, and you get z transform. So you have a 1 over s squared and a 1 over s plus 1. Okay. There. Okay. So from here, this essentially boils down to a typical z transform now. Okay, z transform. And if you recall that in symbol-wise, we always say, okay, when you write z transform x of s is equal to x of t, right? And it's equal to z x of k. Okay, so it depends on the sampling time, of course. Okay, so this is all same. Yeah, and from here, what we can do is, what I can do is I can use partial fraction expansion, and then use the table, the z table, and directly to find the z transform, right? Yeah. So here's what we can do. So we'll partial fraction expansion what's given inside the block at here. Now you do have a 1 over s squared at here. The typical way for when you have a second order here, so you write like that, right? So a over s squared plus b over s, and then c over s plus 1. Okay, so that's partial fraction expansion, right? Yeah. And the a, b, c, they are called residual. Okay, and you can use MATLAB residual function to find a, b, c, or you could find a, b, c by comparing coefficients between this one and this one here. Right? Compare coefficient, basically you rewrite this one all the way back to s squared times s plus 1 as a denominator, and then comparing coefficient for the numerator with this 1 at here, and you'll be able to construct 3 equations to solve for a, b, c. Right? Yeah. So they're not that actually bad. You know, sometimes observation actually could result in this kind of simple case set here. So bottom line is, you can try yourself. The a at here turned out to be 1, b at here is -1, and c at here is 1. Okay, so your a, b, c you can find through all different kind of approaches. You can find a, b, c. So once we find these 3 here, this is the simplest form. So now you can use your z transformation table. And the z table here, you look at, okay, so where's 1 over s is here. Where's 1 over s squared is here. And where is 1 over s plus 1, which is here, right? So 1 over s corresponding to this, 1 over s squared corresponding to that. So now we can write down the z transform for each one of this, right? So the first one is tz over z minus 1 squared. The second one is z over z minus 1. And third one at here, this is a 1 over s plus 1, so the a value is 1. So that gives you z over z minus e to the power negative t. Okay, so those are all basically simply by looking at the tables at here, so you'll be able to write this stuff. Okay, yeah. So technically speaking, this is your that's it. This is your pulse transfer function. Okay, that's your pulse transfer function here. But we usually write it into a fraction format, so you should try to simplify this a little bit. And often in time, you can simplify this. See, the first one here is a z minus 1 over z, right? So this is 1 minus 1 over z. And you do have a z at here inside this big bracket. So that'll cancel this out, right? So to cancel this out, okay. So I'll just write down the results headed here, okay. You will get the results, which is okay. So here's the final results for the Z transform. Yes?
What does the pulse train function, once you have it, what does that allow you to do?
It basically, you create, you start from, basically starting point is a so-called data sample system, right? You know, you have a mixture of continuous and discrete signals set here, okay? Yeah. So with the pulse trans function, then you end up with basically, a formality like this. So I should probably, let's use X of key here and Y of key here. So you end up with a formality like that. So inside this block is this. Right? So it's like basically a continuous control system. And when you have a control system, simple control system, right? And you have an input, let's say X of t and Y of t here, right? Yeah. And you want to simplify this. Basically, you can simplify this to one single block at here with input and here and here, right? Yeah. And this symbol block in this case is GU or 1 minus GH at here, right? Yeah. So the bottom line essentially is you when you design control system, or when you want to analyze the system, the control system design, and you wanted to simulate the response of the system, right? Or you wanted to basically analyze the frequency response or analyze the different characteristic system. So in order to do that, and you have to have a simple block like this, right? Yeah, to describe the input and the output. That makes sense, right? So this pulse trans function is basically the counterpart of the continuous system Laplace trans function for the system, right? So here you have open loop system. This is open loop, right? Yeah, we'll look at the closed loop shortly. Okay. So if you have an open loop system, input and output, how can I predict or describe the system response? So what do? We derive basically first of all, we derive the pulse trans function at here, which is this one, right? And then that pulse trans function essentially relates the input and the output. Okay? So now you can just like a continuous system. So now you can see, okay, if I give the system is a unit step input, then what's the system output, right? If it's an impulse input, and what will be the system output? So now I'm ready to do this because I already have this one now, right? And I can do simulation. I can simulate the output based on different type of inputs. Okay, yeah. And then this one here, right? Basically, it's a representation of the system that's given at here, the simple system. Okay, yeah. Is that clear? Very good. Okay. I want you to remember important results that are here to remember is this one here. Okay, yeah. So basically, if you have a zero order hold and a plant together, you have a one single block, then its Z transform is this. Then you plug in your G of S, and you'll be able to find the overall Z transform. Okay. Yeah. So these are important results to remember. All right. Yeah. Okay. Before we go ahead and look at a couple more examples for open loop at here. Okay. I do want to summarize a little bit. Maybe hopefully to clarify a few connections. Okay. So as you can see right now, I think if you think about the Z transform that we have been conducting at here, it seems that there are different routes, right? We can go around then to get our Z transform, isn't it? Right? We're starting from x of k and of x of z, or we're starting from now we have a x of s and an x of z, and we have x star of s and x of z, right? There's different routes to end up with this x of z here. So here's a couple of comments in here or connections I want to clarify. Okay. So number one, okay, as you think about it, maybe I'll first of all I'll just write down a different type of signal here. So let's say you have a h of s, you have a h star of s, and you could have h of z, right? So this is basically what so far. You could change the h to x to y, so any symbols you want. Okay. But in terms of the type of signal, we see, okay, continuous system, you have h of s, and then after impulse sampling, you have a h star, and then after z transform, you have h of z, right? So the point here is, let's take a look at the connections at here. Okay, yeah. First connection. Let's think about this h of s to h star of s. Right. This is the first connection in here. Okay. Yeah. So from here to here, and the operation you need to do basically, you need to have an impulse sampler, right? You have if this is h of s at here, then you got h star of s. Or this is h of t, then you got h of k at here. So you need to have an impulse sampler to realize this type of conversion. Okay, yeah. So the question here is, what's the connection between these two signals, right? And I think I have an expression in previous lecture that I wrote it down there. So you do have a connection in here. For example, h of s equal to 1 over t. Okay, so as h at here. And if you recall that, we actually call this starred Laplace transform. Okay, starred Laplace transform here. Okay. So that's one thing that we wrote it down here. That's the connection between your h of s and h star of s. Okay, yeah. However, this one is a very mathematical results. Okay, mathematical results. So if you think about it, let's say if we have h of s, and that's very possible because if a continuous system, then you can have this h of s very easily, right? Yeah. Then the question here is, given this one here, then how do we derive an h star of s? Okay, I mean this formula not gonna give you this h star of s. Okay, the kind of h star of s right away actually. Okay, yeah. So what we need to do at here is, okay, we'll rely on another formula, okay, to find this h star of s. So on page 84 to 87 in the textbook, okay, there is a formula to derive for h star of s given this h of s. Okay, so I'll write down that formula without the proof, and you can look at this 3 or 4 pages that are here for the right proof. Okay, so here's the formula for h star of s if h of s is given. Okay, so h star of s equal to this formula. Okay. Okay, let's write it down and then we'll analyze this carefully. Okay. Yeah. H star of S is equal to summation. Okay, summation of what? Summation of residues. Okay, and where the residues from? The residues are from this expression. So h of lambda times 1 over this. And h of lambda basically is from the h of s. So you replaced s with lambda. Okay, that's basically what this means, right? So you see you're given some Laplace transform. So here for this formula, you'll replace the s temporarily with lambda. It's okay? Yeah. And then you will have an expression, okay, by multiplying h lambda with this one. Then we'll look at the residues of this expression. And residues is always about basically, residual. Remember the residual is this, right? The A, B, C is the residues. And residuals essentially associated with what? With basically with the poles of the denominators here, right? So here s squared, there are 2 poles, and repeated at s equal to 0. So your A, B corresponding to the poles at 0, 0. And a C corresponding to the poles at s equal to -1, right? Yeah. So here, basically, I'll give you an example. You'll see much more clear. So here you have an expression which is going to be in the fraction numerator over denominator. And the denominator will tell you basically certain number of poles, right? Yeah. And then that poles will lead to the residue set here. Then the summation, basically you add all the possible residues up. So at the end you got your h star of s. Okay? Right. So that's basically the idea here. Okay? Yeah. So the steps that here basically replace your s with lambda, so you get your h of lambda, right? That's your first step. Okay, and then second step, okay, is from the lambda to here. Okay, so you see here, so the residual of this at the poles of lambda equal to lambda I of h of lambda at here. So basically, the lambda equal to lambda I, which is the poles. This is the poles for h of lambda, for h of lambda, not for this one, it's for only h of lambda here. So find the poles for h of lambda. Depends on the given h of s or h of lambda. You'll see maybe multiple poles, right? How many poles, that depends on the actual question. Okay. Yeah. So, and finally, okay, then you look at the expression, okay, in this red circle here. Look at this expression and find its residues, okay, at lambda equal to lambda I. Okay, so that's basically the steps involved here. All right, yeah. So I'll show you an example. Okay, and then we'll see how do we find the residues and how do we find this h star of s here. Okay, yeah. Okay, so let's see. I have an example here. Have a continuous system h of s, which is 1 over s plus 1 times 1 s plus 2. This is a very simple system, okay? A very simple block. So first step, and we wanted to find h star of s, right? We want to find h star of s here. Okay, yeah. Okay, so first step, so here I want to find h star of s using this formula, using this formula here. So first step, change the s to lambda. You got that? And this is very obvious that the poles that are here, there are only two. One is -1 and the other is -2. Okay. So, and they are real distinct poles in this case, right? Real distinct poles. Okay. So basically, there will be, because there are only two poles, so there will be only two residues, one corresponding to that and one corresponding to this, right? Yeah. So now let's see. So basically, I see only two residues. One is K1, let's call it, and the other one, let's call it K2. Okay, so now I'm going to find K1 and K2, and also you should make a note here. I mean, this is a real distinct. Okay, so real distinct poles that are here. It's actually very simple. So when poles are real and distinct, to find those residues, and you have a formula actually to use. So for example, your K1, right? For the K1, to find this residue right here, so you use your lambda minus your lambda 1. Okay, so lambda minus lambda 1 time h lambda, not time h lambda, times that whole block here, this block now. Okay, times this. Is that good? This is plus. Minus. So see, if I put a -1 here, it's +1. Then you'll cancel my, yeah. Is that good? Yeah. So just be careful here is you're looking for is the residue for this one here, not residual for the original h of lambda, huh? Yeah. If you're only looking for a residual of h of lambda, then you don't multiply this term here, right? But that's different purpose, right? The purpose here is this formula, so that's dictating that you have to multiply this term here. Okay, so I'm gonna then after multiplication and here, you can set your lambda to be lambda 1, and of course, which is basically -1 here. Okay. Yeah, so after you've done it. So let's say inside the big bracket, if I do this, then what comes out of this multiplication here? So lambda minus lambda 1 multiplied by this, I guess you can -1 here, you can put a note -1 here. So this times that, so you cancel this lambda plus 1 on the denominator, and then you have lambda plus 2 left on denominator, and you also have this term here left, right? Okay, so that's the result here, and then you let the remaining lambda to be -1. Okay, yeah. So substitute this lambda to here and here, and -1 plus 2 is 1. Okay, good, it's gone. And then s minus -1 is s plus 1, so we end up with, okay, like that, right? So this is the first residue K1, right? First residue K1. And second residue you can follow very similarly because of real distinct, so the formula is the same. So you use lambda minus lambda 2, and then h of lambda here again, right. And then let lambda equal to lambda 2, which is -2, of course. Okay. So you will end up with, okay, if you do it carefully, s plus 2 at here. So that's K2. Good. So now your overall h star of s is K1 plus K2. Yes. Actually, I will see that there. So, sorry, what's your question again? Is the result the same as what?
As the start of the Foss transform.
You mean like this?
Yeah.
Yes, it will be the same. But if you think about this, if you have this h of s at here, right, and then you use this formula, you don't get the same as this right away, right? Yeah, because it's involving this g omega s here, right? Yeah. So what you want is, you don't want that. This is more of a mathematical results that here, from the, it's from I forgot which page. So this is not the results you want to make use of to derive for the pulse transfer function, right? So here, if you just do the simple put the h of s here and then plus g omega st, you actually you don't get the same results. Behind the thing is the same, but you don't get the same results as you're getting at here. Okay? Yeah. So the point here is, you want to make use of this one here for your h star of s. The ultimate goal is for what? I need to find. The ultimate goal is for h of z, right? Yeah. So you want to use this one to get to here. If you use this one here, you can't get to ultimately here that easy, right? Yeah. So I'll write it down here. You'll see, because there's one more step to go. Okay. Okay. So this is your h star of s now, right? Okay. So remember, the idea is, right? H star of s is, the idea is to get to the h of z. So you have these three signals that are here, right? So from here, here, here. So the idea is to get to this h of z at here, right? Yeah. And we, in the previous lecture, I think I mentioned one common pitfall. There is a connection basically between the s and the z. Okay, when you do the impulse sampling, you have a connection between the s and the z, which is this one, right? Yeah, and this is from impulse sampling. Okay, impulse sampling results. Okay. Now, this one here, and you have s equal to 1 over t ln z equivalently. Okay, yeah. So you have basically a connection between s and the z. So when do we do this substitution then, right? When do we do the substitution? The substitution will only be able to apply it, okay, to the start one, not to the h of s, right? So basically, only at here I can see, okay, so I'm gonna replace the s with the 1 over t ln z. Okay. By doing this replacement, guess what do we get? We get our h of z. Okay. So let's try it, right? Let's try if I do this replacement here. What do we get? You have this e to the power of ts plus 1. Okay. So technically speaking, I can write that into e to the power of ts times e to the power of t. Right? So this term in here, and that term there. Oh, sorry, I missed a negative here, right? There's a negative here. Okay. K2 negative, right?
Wait, no, K2 term, like the entire.
Oh, K2 term is whole thing is negative. Oh yeah, you're right. Yes. Yeah, there should be a negative here, right? Yeah, excellent. Okay. So this should be the negative at here. Okay, beautiful. Okay, so here is e to the power negative ts, and then times e to the power negative t. Here's negative. Then 1 minus e to the power negative ts times e to the power negative 2t. Right. Good. So we're doing this replacement s, right? Doing the replacement s. it's probably actually easy to come back here. So replacement s, basically you're using this expression here. So e to the power ts is z, and guess what e to the power negative ts equal to? Z to the power negative 1, right? Yeah. So now your whole expression here is 1 minus, this is z to the power negative 1, and then e to the power negative t here. Same thing, z to the power negative 1, but this is e to the power negative 2t. Right? Okay. So your h of z, okay, basically is equal to this minus this. A little bit simplification. If you don't like negative 1 in it here, you can use yeah. So you got your h of z. Okay? Yeah. So here is basically starting from h of s, go through the h star of s, and then end up at h of z. Does that make sense? Okay? So, but if you recall, actually, the examples I actually have gone through here. Look at the examples I've gone through. Just gone through this example here. And here's your h of, for example, this is your h of s here, for example, right? Yeah. But I didn't use the formula. I just giving here, isn't it, right? What did I do at here to get this h of z here, or the z function? What did I do? I used the partial fraction expansion, right? And then looking at the tables and to find the corresponding z transform function, right? Yeah. So basically, if I come back to this same question here, here's your h of s. Okay, here's your h of s, and same question. Basically, what is your h of z? So I can literally maybe use the same approach. You know, you're looking for the basically the z transform function, okay, transformation, and your h of s is 1 over s plus 1 and s plus 2. Okay. And let's try the partial fraction expansion, and you get a over that and b over this, okay, and ab are the residuals, right? Okay. And if you use the formula to find a and b, you'll see that a is 1 and b is negative 1. Okay, is negative 1. And now you use the table. So what's the z transform for 1 over s plus 1? And what's z transform for 1 over s plus 2? And that table will clearly give you actually the same results as this. Okay? Yeah, so okay. So you see the connection at here now, right? Yeah. So either way is fine. This is probably the most straightforward way. You know, we're giving h of a certain s block, and you want to find that z block, right? Corresponding example. This is probably most straightforward way. But it does, this one here is another approach, basically another method here, right? To go through the h to h star by applying the star operation, and then you get h of z. Okay. Yeah. So in the exercise assignments, I'll ask you to go through both methods here when you're given s function. Okay. So just this is a very procedural. Really, when you look at this one here, I don't think there's any tricky things. You know, right? You just have to be careful. You know, make sure you have all the expressions write down properly, right? Okay, so in MATLAB, okay, you have a command to help you actually to find the z transform when you're given s block or s function. Okay, so MATLAB there's a command called C2D. Okay, so it's called basically continuous to discrete. Okay. And that's a very useful command. You can always use this command to help you or to verify the results. Okay. So how to use the command at here is basically the same thing. You use the command based on a given S block. So whatever it's given, so maybe it's maybe it's this or maybe it's that, who knows, right? Yeah, so it really depends on the actual question. Okay? Yeah. So so let's say, for example, right? Just for example, it's given like that. So in your MATLAB, you can literally say, okay, let's construct the numerator, which is 1, 1. It's coefficient, right? So it's 1, 1. And denominator, you look at the denominator here. So you can multiply these two out, or you can use the convolute to calculate. You multiply out this s squared plus 5s plus 6. Okay? Not the best kind of LS function because they're posed on the right negative 2. Actually, they're fine. So you look at the denominator here. It's 1, 5, 6. So 1, 5, 6. Okay, that's the denominator. Okay. So then you construct a system using the command called TF. So the TF, you construct the transfer function using the numerator and the denominator. So this way you construct this transfer function, which is this. Alright? Yeah. And once you have the transfer function now, then you can convert, okay, using the C2D to convert this continuous system, okay, into a discrete system. But you have to give the C2D the sampling time, which is TS. Okay? And most importantly, okay, and you had to indicate there's option here. You have to tell the C2D, okay? You have to tell the C2D what type of Z transform you wanted to apply. So there are different options. One of the options is called IMP. Okay? So what does IMP means? So IMP basically means, so for example, right? If this is for example, if this is your H of S set here, okay? This is H of S. When you use IMP, so what it means is, here's your H of S. Okay? What it means is you visualize that you have a impulse sampler in front of this H of S block. Okay? Yeah. So that's basically what impulse sampling is about, right? So you have IMP, meaning you have an impulse sampler right in front of this H of S block. And then this whole thing here will be able to give you this H of Z, which is the C2D result. Is that clear? Okay? It's very tricky. Sometimes people forget that. Okay? Yeah. Now, there's another scenario, right? There's another scenario which is this. So basically, so this is a case. Let's say this is case 1, right? Another case, which is the typical case, you have a zero order hold, and then you have your H of S block. That makes sense, right? So that's the most common case. Then you have your impulse sampler at here, right? You got impulse sampler here. Okay? Yeah. So for C2D, it can handle this kind of case actually quite easy. So you can use C2D. Okay? So you still do basically you still create your H of S like what you did over here, create that transfer function, right? Create the transfer function. Then when you use the C2D at here, S, Y, S, the same transfer function for H of S, and the same, let's say, sampling time. And then the option that you give it here, you call it basically ZOH now, okay? And this time, the C2D will generate a different, basically Z block or Z transfer function. Now this result here, okay, is basically representing a Z block based on the combination of these two together now. Okay, yeah. So the results here, okay, will represent this, which is what we just exercised, right? Yeah. So I encourage you to use this MATLAB command to help you or to verify results in the assignments. Okay, yeah. So in terms of wording here, say when you have sometimes the question probably given is given just h of s, but it wants you to find the zero order hold equivalent. Basically means you have to assuming there's a zero order hold in front of this h of s. And you sometimes say, okay, apply the impulse sampling equivalent. So that basically means there's no zero order holder here. Okay, yeah. So just bear in mind the difference between these two options, right? And what the different results the C2D can generate. Okay, so let's look at another example here. Okay, let's look at an example, and want to get clear with all the different concepts. Okay, before we move on to the closed loop. Yeah. Let's look at another open loop pulse transfer function. Okay, another open loop pulse transfer function. So this one actually it looks similar, but it's different. Okay, so I'll draw the diagram first. So here's a block for this open loop. Input x over t and output y over t, for example. Okay? Yeah. And we're going to try to, let's see, assuming there is a fictitious sampler here, and that gives us basically y star of t, and here's x star of t, right? Yeah. Okay. And we wanted to derive what is the pulse transfer function for this data sample system. Okay. So you look at this block right here, okay, and then if you look at your notes, and it's very similar to what we have exercised in it, right? So if you look at the kind of thing that we have done, so even this one here, it looks similar. It's like this is your G of S block, and then this is your H of S block, isn't it? Right? Yeah. But there's a very subtle difference, which is what? Between these two blocks, now we have extra. We have extra what? Exactly. Right. So there's extra impulse sampler here. The presence of this extra impulse sampler, what will that change to this pulse transfer function, basically? Okay, that's the difference I want you to observe. Huh? Yeah.
Not change anything, because unless it's the exact same time, it's going to output 0.
Okay. So you don't think there should be any change, right? Yeah.
What is following the same principle that the PM star on star is just going to be that star.
Well, unfortunately, your first impression is wrong. It will change, and actually fundamentally change these results set here, right? So this extra impulse sampler, huh? Yeah. So think back the things for this one here. So when you have two blocks connecting series without this extra impulse sampler in between, the pulse transfer function basically is what? Is a Z transform of the multiplication of these two blocks, right? That's basically the results that we have obtained, isn't it, right? So let's take a look at the results set here now. Huh? So I'm going to go through this according to the method that we have used in the previous lecture. I'm starting from all the signals inside this loop to go through this step by step. So I'll label some of the signals temporarily, okay? So let's say here is a U of t. And then here is a U star of t. So basically anything after an impulse sampler, you use a star, right? Yeah? And I think that should be sufficient now. So here's your capital X of S corresponding to that. Here's X star of S corresponding to this. Here is U of S. Here's U star of S. And of course, here is Y star of S. Okay? Yeah. So that's the flow of the signals along this block at here. Okay. Remember, we wanted to derive this. And to derive this, I guess we want to derive this first. And once we get this, we can just simply replace S with 1 over T log Z, and you get that, right? Yeah. So I go through the block step by step. So let's say coming from here first, right? So U of S. Okay, so U of S equal to what? Equal to the signal in front of this block, and then time the G of S. Okay, yeah. So X star times G of S. Is that good? Yeah. Now Y of S, the output at here, okay, the Y of S is equal to the U star of S times H of S. Okay, right. So this is a simple observation based on the given signal flow, right? Okay. Now, if I want to derive turn everything into the star one here. So now I'm gonna apply basically star Laplace transform, right, or operation. So basically means I'm gonna apply the start operation to this one here. Okay. And I'll apply the star operation to this one here. Okay, to this. Okay? Yeah. And once you get this, then you think about the nature of, now think about the property of a star Laplace transform operation. When you have X star times G, so apply the star to here and to here, and the star when it's already star, so it's not going to change, and this is just star here. Okay, and then this one here, same thing. Okay. There. So once you get this, and we can substitute this U star, so substitute this into the second expression. So now I have my Y star of S equal to X star of S, G star of S, and H star of S. H star of S. Okay. Exactly. Right. Yeah. So now you see the results now. So you are looking for is the ratio between Y star and X star. So now the ratio, of course, is G star times H star. Right. Okay. So finally, you can replace S with 1 over T log Z, and you get your YZ over X of Z. In this case, it's a GZ HZ, right? It's a GZ times HZ. So as Simon just pointed out, the difference is previously the pulse trans function is GHZ, but this is GZ times H of Z, right? That's the difference. Okay? Yeah. So the presence of a impulse sampler, okay, is actually very important, especially when we have a closed loop. They might have a presence of impulse sampler at different locations, right? Yeah. Adding one or deleting one will result in completely different results. Okay. Yeah. Okay. Yeah. So just maybe to compare it here, if we have a system which is this, right? Then for this one here, your y of z over x of z is GHZ. Okay? That's the difference here. Okay, that's the difference. It's all good? Yeah. Okay. Excellent. So let's look at one more example here. Okay, this one example more or less similar to one of the assignment question, I think. Okay. In this example, it's not given like the previous one, you know, the blocks in terms of basically already samplers and systems like this. Okay. So in this example, it's given more or less as a description of what's the actual hardware implementation in the system. So here is what happens at here. So let's say you have maybe certain error signals. Okay, so this is part. Maybe this is a part of the whole bigger block, bigger system, closed loop system. Okay, yeah. And then this is continuous here, right? It's continuous. So and you use a analog to digital converter. Basically, this functions as a sampler. Okay, so this analog to digital converter will convert this analog signal into a digital signal. Then the resulted digital signal will be given to a digital filter. Okay, yeah. So digital filter, we call it a filter, but in reality, in actual implementation, and it could be just simple, basically a difference equation. Okay, so it's difference equation. It's just like a differential equation, right? And the difference equation, I think we have seen a few examples of difference equation to realize this filtering functionality. Okay, so and filtering meaning basically you may have just a single integration. That's filtering, right? It's just low pass or high pass. So that's all type of filtering operations. Okay, yeah. And after the digital filter here, it's still digital signal here, right? Yeah, and then you use a digital to analog converter to convert it back to the analog signal, then feed it to the plant. Okay, yeah. So the first question here is, with this actual system, and I want to derive what will be the mathematical representation for this open loop system here. Okay. Yeah, mathematical operation basically means, you know, you want to, okay, so here is already mathematical, that's fine, right? This is already here. But how do I represent this? How do I represent this one here, right? In using the block symbols, okay? Yeah, that's basically what happens. And for the digital filter, we can consider this is a certain very simple digital controller. So for this one here, I can think of this as basically a digital controller. And digital controller, you have a certain Z transfer function, a pulse transfer function representing that digital controller. So it's definitely just a Z block here, right? Yeah. The DA at here, the digital to analog converter. So the function of that, you know, you think about it, it's basically functions in terms of the actual hardware. There's always a register for you to hold whatever values out of this one here temporarily, and then give it to the actual system here, right? Yeah. So the DA here, you can consider this is basically functioning as a zero order hold. Okay. Yeah. So that's this side here. Okay. The A and AD here, as I said, you know, basically it's a sampler, right? Of course, behind the sampler you have the conversion from the analog to digital. So for this one here, you can just simply consider this is a sampler and here, okay? Yeah, or impulse sampling. So that's your mathematical representation for each one of the blocks and here. And then when you have this one here, then we wanted to basically what's the pulse transfer function for this open loop system, right? Yeah, so that's the next step. Let's put on some symbols that are here for us to derive this pulse transfer function. Okay, so then pulse transfer function equal to what? Okay. So suppose the input is E of S, so you have an input E of S here. Let's say suppose the output is a C of S. Okay, C of S. And we can always add a fictitious sampler here to give us C star of S, right? This is star of S. So your E of S is over here. Okay. And you have an impulse sampler. Okay. Okay. So second of all, let's observe a little bit difference in it here, right? Now, what's the difference between this block and the blocks that we actually just exercised? So if you look at the difference, even just consider this difference in here. So this difference is what? This is 0 to whole, this is H of S. These two blocks are literally just all what? Continuous block, right? Yeah. And before this block, you have an impulse sampler right away, isn't it, right? And there's nothing in here, okay? Yeah. But here, the difference is you have an actual digital block, right? Which is functioning as the digital controller, okay? Yeah, so that's a difference in here, right? Yeah. So in terms of the signal labeling in here, and I can label the output, okay? The output of the digital block. Let's call it just call it M of Z, right? M of Z here. And then the input of the block here, I can call it E of Z, okay? E of Z. You could, yes, it's E star, but because of the DZ here, I don't need to use the E star of S anymore, right? Yeah, I don't need this here because this is already a DZ, right? It's a digital block. Digital block use what? Use discrete sequence of numbers to operate, right? Yeah. So, but this M of Z here, now this one here, you can definitely still think there is M star at here, okay? M star of S before this zero order hold, just like this location here, you have whatever, you have fx of t, then you have x star of t here, isn't it, right? Yeah, or x star of s, okay? Yeah. So that would be the signal here, and then here you have maybe some kind of a control signal given in here, so that's fine if we don't have to. So we can, let's call it M bar here, for example. Okay, M bar here. So that will be the labeling of this whole whole loop at here. And now let's go through the loop at here. Let's go through the loop. Okay. So first of all, let's look at this MZ. So from here, MZ equal to the input times the block D of Z. Okay, so that's your MZ here, right? So that's this one, and MZ comes from M star of S, right? Yeah. Okay, and then let's go to M bar at here. Okay, so M bar. Okay. So M bar equal to M star of S time the zero order hold. Okay, the zero order hold here. So the point in here, I think for now, I think it's important to emphasize is when you put things together, they have to be consistent. Okay? You actually you can use MS, for example, times D star basically. Okay, so you cannot times a discrete, mix the discrete and then a continuous two blocks multiply each other, right? Yeah. So star is fine. So M star here is still S function, right? Still from S function here. And finally, let's say the output here, right? The output. And the output is the input at here times m bar at here. M bar. And m bar is this expression, so I can substitute, okay, for the m bar. So I get GP of S times and m star of S. Okay, so that's the output, right? That's the output. We wanted the pulse transfer function, so I'm going to convert everything into star S function by applying the star Laplace transform. So basically, apply this star Laplace transform. And that gives me C star at here. And then over here, right, when you apply the star Laplace transform, okay, when you apply the star Laplace transform, now be careful you don't just apply star here, and star here, right? It's always do what? To combine these two together first, right? Combine these two together first, then you apply the star basically, okay? Yeah. So, for example, let's say for example we call the combination of this is GS at here, okay? Let's call it GS. So now you have your G star times M star at here. Right. So if this is G of S at here, in terms of symbol, right? Just symbol here. Okay. Yeah. So now I can replace all the S to Z. So basically you get the CZ equal to GZ times MZ, right? Times MZ. Okay. And MZ, if you look at the flow of the signal, MZ is already just, you already have it. It's EZ times DZ. So it's GZ EZ times DZ. That's your C of Z at here, right? C of Z. So pulse transfer function is the transfer function between output and input. So CZ over EZ, which is GZ times DZ. Okay, GZ times DZ. DZ, we don't know what it is. You know, in the actual question, you will have it. It's a difference equation, so you will be able to obtain that. And GZ comes from G star of S, and it comes from this guy here, right? It comes from this. So GZ basically the Z transform for the multiplication of these two. Okay, the multiplication of these two. Okay, and if you recall the first example that we have gone through, so for this block right here, I can further simplify this, which is what? 1 minus Z to the power negative 1, and then Z transform GPS over S, right? GPS over S. Okay. So if your actual plan is given, then you can use, you know, partial fraction expansion to find this inverse Z, Z transform, right? Yeah. So that is for this system here. Okay. So let's see. I won't finish this now, but for example, let's say for DZ, okay, or the digital filter. I'll give you. Now we'll look at looking at an actual system at here. Okay, look at actual system. So if this is a digital filter, okay, here's a digital filter here. What's the plant again? The plant. Oh yeah. Here's a digital filter, and then a plant is GP of S equal to 1 over S plus 1. Okay. So here's a concrete system now. So you have a digital filter, you have a plant here. Okay. Then what will be the CZ over EZ? Okay. Yeah. So let's try. We'll finish this. I think I'll finish this next lecture here. So given this and that, and what is this? And we can also simulate the response of the system based on the actual digital controller and the actual plant. Okay. All right. Any questions? Good. All right. We'll see you next week.